So why are the Bayesian computations possible when ML computations are not? Just to understand that a little bit deeper, ML works with a joint distribution of all variables to find parameter values that give the likelihood maximum. So joint distribution of all variables, say all of those binary factor indicators that I just mentioned. Bayes doesn't need to consider that. It considers a series of conditional distributions. It's not conditional distributions for the variables, but conditional distributions for the unknowns. That is, for the parameters, for instance. A series of conditional distributions, breaking it down in a series of conditional distributions, is computationally much easier to deal with than the ML description of the joint distribution of all variables. The joint distribution can be difficult, conditional distribution can be easier. That's the main reason. What are we talking about when we talk about priors? Let's take a moment to just be sure about that. And first note that the default of Mplus is non-informative priors. But let me first tell you what informative priors are. So on the x-axis here we consider one parameter, and we want to find the best estimate of that parameter. We want to find a point on this x-axis that we can call the parameter estimate value. And if you use maximum likelihood, the likelihood it has a peak somewhere, hopefully very well defined. That is the point on the x-axis where the first order derivative is 0, where it's flat here. The second order derivative has to be of a certain kind, so it's not a minimum, instead of an optimum. That's an I case. So the ML estimate would be here. So if you don't mind, you should scribble here. This could be theta hat or whatever you want to call the parameter, but hat it should be, that is the M, and then subscript ML estimate of the parameter. Now what Bayesians do, as opposed to frequentists like maximum likelihood analysts, well, let me back up. Maximum likelihood people, frequentists consider parameters as something fixed. It's a fixed unknown quantity. Bayesians consider parameters as distributions, as random variables that have a prior distribution where the most likely value here is here at the top, at the peak of the prior, but based on previous analysis and substantive theories, but mostly, I hope, previous analysis from real data, you have a fairly good notion about approximately what the estimate might be, what the parameter value might be. So the peak is here, but you're not saying that you know exactly that it's here, but you put a little bit of a variance around it. The smaller the variance, the stronger your belief, the prior information that you have. The larger the variance, the less you believe that you know where the estimate would land. So what Bayes does is to weigh together the likelihood from maximum likelihood with the prior to get a posterior. And that's obtained by the so-called Bayes theorem, a very simple theorem for going backwards. That's how my short-term description of it. It's in the book, our new regression and mediation book, if you want to read about Bayes. Now, you may not like to use prior information, even if it's solidly based on previous studies. You want to start from scratch. Well, in that case, you should use non-informative priors, the default of Mplus, which means that the prior has a very large variance and almost doesn't change the information contained from the data in the likelihood, so that the posterior and the likelihood have their peaks at approximately the same parameter value. That's what Mplus does by default. Non-informative prior. Even though it's not informative, the computing algorithm is totally different than the maximum likelihood computing algorithm. And you get these speed advantages that I mentioned. So we have non-informative priors, also called diffuse priors. They have very large variance. It's huge in Mplus. I forget what it is, but very large. Reflecting uncertainty, large uncertainty in parameter value. And we have informative priors at the bottom here, reflecting prior beliefs in likely parameter values, which may come from substantive theory combined with previous studies of similar populations. Think meta-analysis, where you do a repeated set of interventions, for instance, in the same population, and you look at the intervention effect, and you have a pretty good notion about how big it's going to be, but it varies a little bit. So you have a prior with its variance. Weakly informative priors are also used in Mplus, actually for thresholds in categorical variable outcomes, because thresholds sometimes need a little extra assistance so that the iterations moving towards convergence don't veer off into some strange areas. Actually, that's very similar to maximum likelihood, especially, for instance, in IRT with the 3PL model, the 3-parameter logistic model with guessing parameter. The guessing parameter is one of those parameters that need assistance in its estimation. They have a little penalty function in maximum likelihood in most IRT programs to guide the convergence to the right parameter estimate. This works very much the same in the base. But we use that very sparingly, although it's a great idea for some applications. Saying that we don't want parameter estimates to go off into an impossible area, a totally ridiculous area. Andrew Gelman has written about that very much. Actually, he had a big article in JRS's, Journal of Royal Statistical Society. The paper was read in London and lots of comments. It just came out in JRS's A or B. It's a nice discussion about using weakly informative priors. Now, the real advantage of Bayes that you should not be afraid of using someday when you're ready for it, but not first, is using informative priors. Frequencies don't like that. They think then Bayes becomes subjective instead of objective, not only using the data objectively, but using prior information or beliefs. But I would argue that frequentists already do use informative priors in many cases, although in unrealistic ways. A pertinent example for us is CFA, confirmatory factor analysis, where we specify a lot of fixed zero loadings. And we say that's based on theory, but the theory cannot be so strong as to say that it's exactly zero. Instead, you can imagine a prior which has mean zero and perhaps a very small variance around it, but still a little bit of wiggle room so that the theory is better the analysis better matches the theory. Theory is not that precise. So you can do this informative priors in confirmatory factor analysis in Mplus since version 6, actually. And that's what we call BSEM, a special Bayesian approach to SEM, which was published in 2012, I think, in Psychological Methods. So it's on our website. The advantage of posterior distributions with informative priors is that the credibility interval is, that is, the Bayesian confidence interval is shorter. You have more precise statements.